Okay, so this is exploratory online seminar number 72. Today, I like to present how to use exploratory series part 3 and analytics. Okay, so let me introduce myself. My name is Kan Nishida, CEO at Exploratory. Exploratory is a company we started in spring 2016 to democratize data science. Prior to that, I used to be working at the Oracle, building and delivering various data science related products. So our vision as Exploratory is that anyone should be able to make data-informed decisions. So our mission is to democratize data science to help people make better decisions with the data. So when we say data science, we think it's like this sort of like 5 pillars: data access, data wrangling, visualization, analytics, and communications. These 5 things are important to not only answer business questions, but also make better decisions. So I think the way we think about data science is always around decision making. And then we build Exploratory to make these 5 things and easier and more efficient through the modern and simple UI. Okay, that's enough for the Exploratory and myself introductions, and let's get started. So Exploratory online seminar number 72, how to use Exploratory series, part 3. This time I like to introduce analytics. More precisely, like it's sort of like how you can get started. So there's a bunch of analytics types or like algorithms that you can actually use in Exploratory, but there are just so many. So sometimes if you just start using Exploratory, it might be overwhelming. And in this 60-minute seminar, it's not possible to introduce all of them. In fact, if you go to Analytics tab in Exploratory, there are tons of things you can do. But today, I like to focus on this prediction model part, or like maybe you might call it like machine learning, or supervised learning models, or statistical learning model. Whatever that word could be, essentially is to building a model. 2 things you can do with this. One is, of course, you can predict that maybe some kind of outcome, or I think this is more actual practical use cases, is that like to understand the relationship among the variables and then gaining that useful insights from the models. So I'm going to go down more details on this. Okay. Anyway, so if you start using Exploratory, sort of like how you can create a prediction model, either to predict or analyze the relationships among the variables. Okay. So here's our agenda. I'm going to introduce a prediction model. And then I'm going to touch on the correlation association, which is a very important, sort of like a fundamental under the prediction model. And then start getting into like Exploratory using a summary view to investigate the correlation, and then create a prediction model based on such relationship, and then also interpret what the model is saying. And at the end, I like to use that prediction model that we build to predict against the data that we don't know the answer for. Okay, so let's start with the prediction model. So prediction model is basically like we have the data that have answers. We say answers, but maybe the label or something like that. Usually like it can be like a numerical values or text values or true or false, those type of logical values. For what we are interested in, so usually like you might be interested in sales numbers or maybe the orders or conversion. If this customer was converted or not, or maybe if you have an employee data attrition, this employee has quit or not, and that type of data. Then use algorithms, machine learning algorithms, to detect the relationship or patterns in the data to identify the answers that can be used to answer answers, and then model them as formula or rules. Okay, so for the statistical learning model is a formula, and the machine learning model is a rules, but that's a kind of too detail on that. So whatever that could be, is important part is like try to have the computer dig into the data, find the patterns, and then define that as a some kind of thing. It's called model, but underlying it can be the more formula or rules. And the last part is basically use that models to predict the answers for the data that doesn't have the answers. Okay. So the use case is that, like, obviously, maybe like let's use the customer data or something, and then maybe like SaaS or subscription business case. And then we know who converted as paid customers and also who didn't convert in the past, right? So like we have like 100 customer data, 1,000 customer data, whatever that would be. And then we have customer attribute data that can be age, that can be how many times this customer used this particular feature in a trial period or something, or what type of regions or the web browser type or they're using or something like that. So those are the customer attribute data. And then based on these attribute data, can we predict which customer is more likely to convert, or in this case, a lead customers that hasn't converted to paid customer, which lead customer is more likely to convert or not, right? So that type of things is a very common use case. Okay, so let's say like we have the data, so the conversion is at the most left-hand side, and it can be true or false in this case. And then age, time, country, and industry. Maybe time is how many minutes like this, customers or like users spend by using, particular service or software and then whatever that could be. Okay, and then what we want to know is this a conversion, right? So like if this customer converted or not, so like it's true or false. And then based on these attributes, customer attributes can be age, time, country, industry. Okay, and we call the special name for this. So what we want to know is a target variable. And then based on the attributes things, those are like predictor variables. So based on these predictor variables, we want to build a model to predict this target variable. Okay. And then building a prediction model, basically like, so you give the data to the algorithm. This algorithm can be, linear regression model, linear regression, logistic regression, or XGBoost, or whatever that could be. And then the algorithm, like I said before, take a look at the data or dig in the data and find the patterns, and then define the pattern as a some sort of like reproducible thing. So can be the formula, can be the set of rules and stuff. And then once that's done, it becomes a model. Then you have the model. This is called prediction model. Then at this point, you can give the new data that doesn't have the data, doesn't have the answer, and then model look at those attributes, which is predictor variables, and then use that, can be formula or set of rules, and then reach the conclusion, which is basically predict the conversion status can be true or false. So based on, for example, this, given customer or given user, hey, this person's age is 25, and then the country is, Japan, industry is advertisement. Therefore, according to this formula that we already defined, this customer is more likely convert or more likely not convert or something like that. Okay, so that's that. That's a kind of like a very, very basic of how the prediction model works. So now we want to, okay, like we got it. So like prediction model sounds cool. So which algorithm we should use? Well, that all depends on what the data type of the target variable. So let's say like you're interested in the sales numbers or something like that. So that is a numerical. Then go to the left, and then in the numerical, there are more algorithms, but this is a kind of like a brief version of it. And also these are the ones that are supported in exploratory. So for example, it's a numeric. So then it can be linear regression if you want to go with the statistical learning. If you want to go with machine learning, there's a random forest XGBoost. In exploratory, there's a decision tree and as well. If the target variable is something like the conversion, like we saw, so like it can be true or false. Then go to the center, and then it can be, if you want to go to statistical learning, then logistic regression. If you want to go to machine learning, random forest, XGBoost, and so on. And then the right-hand side says true or false, which means logical, right? So it's this person has quit or not quit. But that there's also time element. How long does it take for this person to quit? Maybe some people quit in 3 months, some people quit in 3 years. And those things, as even though the same status, should be considered as a different thing. So that type of things usually takes like a survival analysis. In the survival analysis umbrella, there's a Cox regression and a survival forest. Okay, so the most common is the left-hand side, left two, so numeric and true false. And then today, we're going to use this more like a true, that numeric thing as an example. Nonetheless, so here's a prediction model. Then at the bottom of this red square, it says time series analysis. Under that, there is Prophet and also ARIMA. These are kind of special type of a prediction model, which is basically try to dig in, not the customer attribute kind of other variables, even though you can bring those in, but the main component is the seasonality or the trend in that time sensitive data. Okay, so but nonetheless, that can be also considered as a prediction model. Okay, so like I said, like a model, you remember the algorithm digging the data and then find a pattern and then define that as a reproducible model, which is can be formula or set of rules. So what is this pattern, right? So that is the one that the next topic, association and correlation. Okay, so association and correlation, basically both of them, basically the same thing, that a relationship where changes in one variable happen along with changes in another variable with a certain rule. And the association is any type of relationship between two variables. And the correlation is a certain type of association. What kind of type, which is usually the linear relationship, but the more important thing is the variables we are interested in happen to be numerical variables. So not like a categorical, not like a text or logical, that kind of stuff. But to me, that's too kind of like academic thing. So usual word we use in a real life, like we tend to call it those kind of things, just correlation in a broader meaning. So don't get hung up on this like a difference between association and correlation in a very strict way. But just kind of briefly say like, okay, so one variable is a categorical, such as country, right? So like US, UK, Japan, and then maybe depends on the country's monthly income could be different, even though in the same organization or same company. So in this case, one is a category and the other is a numeric. So, okay, let's call it association. But to me personally, like, okay, this is correlation too, because that's the kind of word we use in real life. But correlation here is like a x-axis now is age, and then monthly income is a y-axis. So the relationship between these two, and both of them are numeric, right? So it's called correlation. And then for these two of them, two variables are numeric, we can calculate the strengths of correlation. So this correlation is efficient in precise word. That ranges from -1 to 1. -1 is the most strong or strongest negative correlation, meaning one variable goes up and then the other variable goes down, opposite way of moving. And then at the middle is 0. When you have 0, that means both variables have no relationship between one to another. So, and then, so we call it no correlation. Or sometimes we call it independent because both of them don't care each other. And then the most right-hand side is the strongest positive correlation. Like so one is the strongest. So that means one variable goes up, the other variable goes up, one variable goes down, the other variable goes down. And then so we use this as a strength of correlation. So now why association and correlation is such important? Well, this is actually the foundation for building a prediction model. But so what that really mean? Well, the variables that we are interested in varies, right? So it's never be like on the same value. So for example, let's take like monthly income or something of the one a given company. And then some people get paid like $1,000 a month, or some people get paid $20,000 a month. So even though like there's something called average or mean, that doesn't mean that everybody getting the same amount of the money. That people are different. So this type of thing we call it variance. And this is a histogram view of showing all these employees' monthly income. The y-axis is the number of the people, and x-axis is the monthly income. Okay, so why there's this variance? What makes this type of the variance on the monthly income, for example? So bring that to kind of a vertical, the bottom as the lowest, the top is the highest income. So this is a variance. We call this variance uncertainty. I like this word because it sounds kind of smart, but uncertainty is really we don't know, right? So for example, if somebody asks me like, hey, well, what would be the monthly income for any employee? Well, I have to say, well, it depends. It can be 1,000, it can be 20,000. We don't know. But if there is a correlation between working years, how many years this person is working at this company, and monthly income, then that means if I know a given person how working years, then let's say this person has already been working at this company for 20 years or something, then I can say, well, maybe then this person's income can be around 15,000, maybe like between like $13,000 to $17,000 or something like that. So what just happened is the uncertainty reduced. Used to be, I think the value left-hand side is kind of like a weird value now. That was a typo, but it used to be between 1,000 to 20,000. Now I can just kind of reduce the uncertainty to around 15,000. Right. So this is same thing for the association that is like between the category and the numeric. So like a country as the x-axis. Then if the US employee and the UK and the Japan employees, they are all somehow getting paid in a different range, then that means if I know that where this person coming from for this given person, employee, then I can answer better than not knowing, right? So this too, if there is association between the monthly income and the country, then that basically it is reducing the uncertainty. So that's why this is important for building a prediction model, because better understanding of the correlation association, or if there is a correlation association in the data, then we can use that as part of the formula or set of rules. So then if we can find such strong correlations, then it makes it easier to explain, in this case, how the income changes in this organization. And not only being able to explain, but also use that knowledge to predict what the income would be for a given employee. Okay, so that's a basic of prediction model, sort of like a mechanism. Then I guess the important thing is to investigate the correlation. Well, you can start creating a prediction model right away, but I would say like it's important to see like what type of correlation are in the data. So that's sort of like the first step when you start using exploratory. Instead of getting to the prediction model right away, I think that finding a correlation would be the kind of like a natural first step. But not only that, like I'm finding more users of exploratory tend to kind of focus on the correlation. I mean, like start with the correlation, even though that their end goal is to building the prediction model, but always start with finding a correlation. So I'm going to use this employee data. There are a bunch of columns, and then those columns are employees' attributes. Okay. And then there's one column called monthly income. That would be the target column, which means we're interested in how the income changes among the employees. We want to find out like what makes income higher or what makes income lower. Okay, so from here, like I'm gonna get into kind of a demo phase. So here's the employee data. I have open, and then here we have 26 columns and 147 rows. That means 147 employees. And then here is the monthly income. That's the target variable. That's what we want to know. And then, so now let's find out. So there are a couple of ways of finding the correlation between monthly income. One is to go to the chart, and that's a very typical way. Either use a scatter plot or maybe like a box plot type of the charts to find the relationship between monthly income and other variable. But in exploratory, in this summary view, it's much easier way to find out. So you click on this correlate button, and then that actually, I'm going to just set to the default because before this seminar, I was playing around. So anyway, so if you first time open this correlation mode, then this is what you see. And then, so first thing you want to do is this, here's you can set the target variable. So in this case, let's set a monthly income. And what just happened is basically did all the calculations behind the scene to about the relationship between the monthly income and all other variables. So for example, first one is monthly income and age. This chart is basically showing you the relationship between these two variables. So x-axis is age and y-axis is monthly income. All the charts is basically the same logic. Always y-axis is the target variable values. Okay. But you can see that when the age increase, then this is like the line is indicating the average or mean of monthly income in a given section. So x-axis is divided into 10 sections. Okay, from minimum age to max age, probably like 18 to 60 or something like that, and then divided by 10. So each section would be like about 5 years or so. And in that section, we calculate the average of the monthly income. So that's what we are seeing. And then the average income keeps increasing up to this point. So looks like we can say there's some kind of relationship between a monthly income and age. Seems like a positive correlation or something. And then when you see at the bottom, there's a couple metrics. The bottom is here is correlation, 0.4979. This means about 0.5. That's a correlation coefficient, correlation efficient. Okay, so relatively, I wouldn't call it like a super strong, but relative a certain amount of correlation going on between age and the monthly income. Okay, so now next question would be, sorry, so this is a numerical variable. Next one here is, it says attrition, but this one, the data type is character. So therefore, when the character data type, it's instead of line chart, it becomes, this is something called like an error bar. Error bar is that basically showing the average of each value of the category. In this case, a true or false, yes or no. Other variable, when you look at it, there are values of the variable. Okay, and then in each variable's average of monthly income is the one you can see here. Okay, so that means here the 6,832. That is the average monthly income for the people who are no to attrition. That means the people who didn't left the company yet. Okay, so now there's one thing I forgot to tell you about, which is it's kind of a weird concept here. Is something called confidence interval or 95% confidence interval. Okay, so basically, like you see, like this mean line. That line indicates the mean or average for each section. Then there's this kind of area or band showing around the line. So what is this? So this is confidence interval. So what is confidence interval? This is actually really, really important. Even like for the categorical, in this case, not the band, but it's actually the line surrounding the circle. So I want to just quickly explain to you like what the confidence interval is. It's actually kind of complicated if you go really, really deep, but I want to give you kind of a highlight of that. So we have the data, right? So in this employee data or something like that, whatever the data you have in your hands or in exploratory, that is considered as a sample. And then the data that you don't have, however, that probably that, if it's possible, all the targeted, maybe like people or products or whatever that could be, all possible things that happen to be not captured and available to you, but it can be. So that is called population. So for example, in this case, we have the employee data. And then yes, for sure, like, hey, we have only 100 employee and I have 100 employee data. So therefore, the population is 100. Well, that you can think that way as well, but the way you think in the statistical world, that's a sample because the kind of people come to your organization can be outside organization. For example, like, hey, like we accept, the people from this type of the school or this type of the background, this kind of experience or this type of the age group or whatever that can be a lot outside organization, but you happen to, have this, particular people, like say Tom or Susie or whatever. Okay, so that can be kind of like a candidate, but also is like all possible people. If the customer case is like all targeted customers that you don't have the data for them, but they come in the future, but not today. Okay, so that's a population and a sample. So most case, you have the sample data and the mean, right? So like let's say, hey, this group, I have the data here and the average salary, right? Or mean salary is $5,200. Okay, but you don't know that true mean, which is the mean of population, because population data is like you don't have. That's somewhere else. But all possible data is you don't know. Only God knows, or something like that. But you want to guess it. Okay, so beyond what you have, what could be the actual, like the true mean? And then, you never know, but however, so like here is like we have the mean of this data in the orange dot, 5,200, and the true mean, which we don't know, and we are not gonna know. We never be able to know because we never be able to get all people's data. We can only estimate or guess, okay? Then if that's the case, can we have something, some kind of a range, we call it confidence interval, or margin of error, or whatever the name could be. Can we have some kind of range? So then instead of saying like, our, company's average or our company's customers average age or whatever that could be is, using one single value, which could be mean, or which could be ratio, which could be any like a summarized value. Instead of saying that, like maybe we can say, well, probably from like 4,900 to 5,500 or something like that. Can we say like a kind of a range? And then we call it like 95% confidential interval. That means maybe 95% of the chance the true mean can decide within this range. Okay, so this is how like you can deal with uncertainty in statistics. Okay, so what this 95% means is, like I said, like there's a population sample. Okay, and in this case, we have only one sample, which is the actual data. But let's imagine in this sort of kind of statistical way that then we have the population data, and then we can assume, hey, we can sample, meaning like it's kind of randomly selecting, like let's say like 100 people, and then calculate the mean and calculate the 95% confidence interval, which there's a formula to calculate that. And then if you repeat that, let's say 100 times, maybe like 90, not maybe, like 100 times, then 95% of that 100 confidence interval should include the true mean. So what that means, so it's something like this, right? So like you take the sample 100 times, and then like every time like you do it, like you calculate, this is like an all imaginary thing. You're never gonna do it because you don't have it's not possible to identify the population data in the first place. But if we did, this is a kind of theoretical story, then like you can calculate, let's say like you calculate the mean and then calculate the confidence interval, right? 95% in confidence interval. And then maybe some of them might not contain the true mean, but most of them, like the 95% of them should include the true mean. So that's, and then like we happen to be looking at the one of those 100 or 1,000 can be, whatever the number is. Okay, so in summary, the 95% confidence interval, or confidence interval meaning is like instead of using one single summarized value, let's give the range so that we can say, hey, the true mean, even though there's some kind of errors, but suppose this fits in this range. And then 95% interval, a confidence interval, meaning if you do sample 100 times from the same population, then 95 of them should include the true mean, even though we don't know true mean, but we can just estimate. Okay, so having said that, so this band on the left-hand side and also the bar on the right-hand side, the difference is a numerical data type variable or character data type variable. These are 95% confidence interval. So that means that true mean should reside in this range. And also this band or this length or like a range becomes bigger when you have less data, and it becomes smaller when you have more data. So that's actually one important characteristics. So whenever like you see like longer one, the confidence interval longer one, that means, for example, the age-wise, or looks like the people, older than 40 or 45 in this data, there are not many in this data. However, there are many, probably like many data in between age of 20 to 35 or something. Okay, so having said that, now that we know how to read the chart part, and then the bottom, there's R squared, p-value, and then a correlation, sometimes unique value if it's the data type is character. So what are these? So the correlation, we already talked about that. So we can actually sort by the correlation. So here, we can sort this variable from the strongest correlation to weakest correlation, right? So here, like select the correlation, and then we just sort by this value. So for example, job level correlation between monthly income and job level is 0.95, which is close to 1. So it's a very strong positive correlation. Next one is the total working years, and age. Age happens to be the number 3. Okay. And then, so this is one way to do it, but then there are two problems. Number one, correlation value can be range from -1 to 1. This sorting is down from the highest number to lowest number. That means the positive ones should show up here, but how about the negative one? How about the negative correlation, but strong correlation? So in this data, when you go here, the correlation goes down, and once past 0, and then now like here, you see like minus 0 point something here, and then towards the end, there's a minus 0.45. And then minus 0.45 is relatively strong correlation that just happened to be negative. But when you're trying to find the relationship between a given variable to monthly income, you probably don't care if it's negative or positive. Like you want to find a strong relationship. So this can be misleading because your eyes as a human like tend to focus on the top one, like at the top left kind of corner. So that's one problem because of negative and positive when you sort. Another problem is for the categorical, for example, something like this, attrition or education field or whatever, we can't calculate the correlation in the same way we calculate the correlation for numericals. So therefore, in exploratory, there is no correlation values here, not just exploratory. You can typically, like, you can't calculate. There work around to it, but in practically, like, you can't. So therefore, there is no correlation value here. So that means these might have strong relationship with monthly income, but happen to be like sorted position at the very end. So you might get impression that, oh, these have no relationship, but they are. So in order to overcome those two problems, there's something called R squared. And R squared is basically the square of this correlation. So this correlation coefficient value is sometimes called R. So that's why like R squared, that name is coming from. So we can actually use this because when you square, minus becomes plus or negative becomes positive. So so that's, you solve the first problem. Second problem is that for the this categorical stuff, right? And you can actually calculate R square even for the character data type, even for like other, maybe can be the logical data type, because in exploratory, it builds a linear regression model behind the scene for every single variable. Okay, the target variable is monthly income, and then the predictor variable is that, for example, in this case, education field. Once you build it, the linear regression model, then you can calculate the R square, or typically like a linear regression model returns R square already being as part of the model. So therefore, we have the R square for even a character data type. That means we can sort by the R square, not the correlation. And I think this is a best way to sort all the variables. If you're interested in finding what are the variables have the strongest relationship with monthly income or the target variable. Okay, so in this case, the job level is still number one, and number two now is the job role. See, this is a character data type, but because R square can be calculated by building a linear regression model behind the scene, that's why it says linear here. So now like this is number two, and then number three, the total working years, and the age as a number four. Okay, so it seems like these four variables have a stronger relationship. So there's three metrics. One metrics I haven't explained yet is the p-value bracket KW test. This KW meaning classical Wallis test. Probably my pronunciation is now doing a good job here, but this is one of the statistical tests to test the relationship that we observe in front of our eyes is significant or not. And what that means is sometimes there might be some relationship, right? Like, so let's say maybe good example, maybe, let's pick something like this. So looks like a percent salary hike, and then maybe like work-life balance or something. So it seems like going upwards. So like work-life balance, score is higher, then the salary might increase. But is that increase is something that can be reproducible, or can even like the data, similar data kind of shuffle, or like maybe new employee come to this organization, still like that theory can be reproducible or not. So is that difference is meaningful? We should pay more attention to it, or the difference is kind of like tiny? So that if the difference is tiny, then we don't call it like that's significant. So if it's a difference is kind of like a sort of measurable and reproducible, then that difference is significant. So that type of the test is something that you can do under the analytics too, but here is automatically done behind the scene. So the way to understand here is it says less than 0.0001. So which this mean is starting with something called null hypothesis. This is kind of getting a little too detailed, but if we assume there's no relationship between job level and monthly income, the relationship I'm talking about here is a correlation or association type of relationship. If we assume there's no relationship between these two variables, what is the chance or probability that we see this type of relationship, or maybe like this correlation value 0.95? And that is almost like a zero. So less than 0.0001. So that means almost like that's not going to happen. But it's happening here. So that means something that shouldn't happen is happening here. That means the assumption is wrong, right? So then we can reject the assumption. The assumption is like no relationship. So if you reject the relationship, that means the opposite. Oh, there are some relationship here. So that means the job level and monthly income relationship is statistically significant. That's the conclusion. But this test is basically telling you is that this relationship is significant or not. It's like a binary. It's like a 0 or 1, right? And then what kind of relationship that is? Well, correlation-wise, 0.95 is a very strong relationship. So if you're interested in the strength of relationship, then you want to focus on this correlation or R square. But if you want to conclude if the relationship is significant or not, that kind of like a yes or no answer, you want to look at this p-value. So p-value is like a guideline. Somebody said in a long time ago, 0.05, which is 5%. So that's kind of as a guideline. But the important thing is like if the less chance, let's say like closer to 0, but then that means significant. If you see something like here, 0.43, that means 43% chance, or 0.56, 56% chance. That means even the assumption is right. That means there is no relationship between work-life balance and the monthly income. This kind of change, this kind of relationship can happen out of like 50% of the chance. So it's still like assumption is valid. It's not that kind of strange assumption. So that means we can continue with that assumption. Basically, work-life balance doesn't have any relationship with monthly income. Okay, so those a lot of things you can learn from this summary view, the correlation view. That's why I strongly recommend use this correlation bottom to start with. Okay, so another thing is that here's attrition, and then the correlation view supports only the numerical target or logical target. And what if like I don't have logical? Well, logical is always you can create very quickly. For example, typical thing is like a customer has churned or has customer converted. In this case, employee quit or not. Sometimes comes as a yes or no. Sometimes comes as a 0 or 1 or a different type of the text. You can quickly convert this to logical data type. So from the column header menu, if it's yes or no or 0 or 1, and you can select just a change data type and then convert to logical, and then click run. And automatically yes becomes true, no becomes false. 1 becomes true, and 0 becomes false. And you can actually specify like which one to be true, which one to be false. Or you can convert, for example, this type of numerical, let's say like a greater than 5,000 should be true, less than 5,000 should be false. You can do that as well. But in this case, we have now like a logical target variable. Then I can go to the correlation view, again, correlation mode, and then select that like attrition. Now like I can select it because it's a logical data type. And the same thing, like you can understand the relationship between the target and all other variables. One thing though, to sort these variables, we don't have correlation or R squared. Those are only for numerical target values. So instead, we have something called AUC. I'm not going to go into the detail of the AUC, but it's the brief explanation is that how efficient a given variable can separate true data and false data. So which means basically indicate the strengths of the relationship or correlation. I'm using a broader sense of the meaning of the correlation, but correlation between job role and attrition. And the AUC is 0.67. So an AUC range from 0.5 to 1. 1 is the strongest. 0.5 is the weakest. Okay, so so job role, total working years, monthly income seems like these 3 variables, or even like 4 variables, how many ever that could be, have some sort of relationship with attrition. Okay, so that's the logical data type case. I'm going to go back to the numerical, the monthly income. Okay, so now we have we investigated the relationship between the variables, this specifically the monthly income, right? So now here, what I want to do is create a prediction model and interpret the model things. So I realized that we have only 15 minutes left, so not possible to go into detail of the interpreting the model, but I think we can cover some of it. So let's go back to exploratory. So here we know this age sorry, like I should sort by the R square. So this job level, job role, total working years, age, these variables have the good, strong relationship with monthly income. So can we use these four variables to predict the, what the monthly income would be, right? So in that case, I can select by using Shift key or Command or Control key to select multiple columns, right? And then note the monthly income as a target variable in this case. Then from any of those column header menu, then when you click on this downward arrow, you see type of algorithms. So first one is the linear regression. Like I'm going to use this one. So if I click this, then what's going to happen is it is going to create a linear regression model based on these four variables, predictor variables. Okay, and then the target variable is monthly income, which basically did is a kind of a shortcut of going to the analytics view, and you can create this linear regression model from scratch by assigning the columns, but it was just a shortcut. Okay, and then the first thing you see is the prediction tab, and then this tab actually is pretty useful because you can see like, hey, like here's the job level. What happened when job level become from 2 to 3 or 3 to 4? How much monthly income change and what the monthly income would be? How about a job role? If the manager, what would be the income would be? If it's a human resource, what would be the income would be. So this blue dot or blue line is the predicted values, and then the gray line is actual value. And this gray line is the one you are actually seeing in the summary view here. So these line or this error bar, these are the one basically shown as a gray line or a gray bar, error bar. Okay, and then the blue is actually the predicted values based on this prediction, like a linear regression model. Okay, and then when you go to the importance, which it shows which variables are more important than the others. So here, like it says job level, this is like a y-axis, a relative importance compared to other variables. So it doesn't, like this 18 million doesn't really mean anything particular, but it shows how strong the relationship compared to others. So it seems like job level and job role, if we know these two things, then we should be able to predict monthly income better. Okay, so that's this is actually pretty useful. And then another tab I'd like to introduce is the coefficient. This coefficient, what this one's saying is that, for example, this job level, and it says coefficient 2,768 dot something, something, something. Okay, so this one is a coefficient, but also can be considered a slope of the in this linear regression case. What slope? Remember 2,768? If I go back to the prediction tab, the slope of this line. Okay, so when you move from one level, from job level 3 to 4, how much will the salary increase? That is a 2,700. If we move from 4 to 5, how much salary increase? That's a 2,700. Okay, so that slope of this blue line is the one basically showing as a coefficient. Okay, and then when you notice though, if the slope is positive, you see the blue color. Slope is negative, you see red color. How about this gray thing? What is gray thing? Well, for example, look at the age. Somehow age is coefficient -3, and it's a gray color. And the gray color says p-value 0.0 less than 0.05, greater than 0.05, meaning this one, the p-value is 0.75. So same statistical test, not exactly the same, but that statistical test is done here as well to see if the relationship between age and monthly income is significant or not. Okay, and then this one is considered is not significant because the p-value is too high. Okay, and then why it's too high? Because this type of relationship can be observed as a sort of a kind of like by chance, not because of the age, but maybe because of the monthly income varied in the first place. Okay, so that's kind of weird because you'd say, but I know age has a relationship. Age and income has a relationship. I mean, like, hey, didn't you say the correlation 0.49? Like this 0.49 is nothing. And also, like, hey, it says p-value is less than 0.0001. So it's significant. And why now you're telling me that it's not significant? And that is kind of a really fun part of this analysis here. So this is Ralph Waldo Emerson's comment. He's an author, American author. And shallow men believe in luck or in circumstance, but strong men believe in cause and effect. So when you look at something like this, and like ice cream and shark attacks, and then like somebody's counting those numbers, and from May to July, both of them going up, right? So then you might think, oh, okay, it seems like if you sell more ice cream and then more people get shark attack, or maybe more people get shark attack, that means we can expect our ice cream sales goes up or something like that. Of course, probably you don't, but when you see the chart like that, then oh, okay, there's a correlation. That means one increase and cause the other one to increase. Right. But it turned out there's something called confounding. So it turned out the temperature is the one who's causing the now increase of shark attack and an increase of ice cream sales. Okay, so ice cream sales goes up. That's kind of intuitively easy to understand. But the shark attack too, because more people go into the water or ocean, and so there are more chance to encounter shark, right? So therefore, shark attack goes up. So that says we got to be careful when you see the correlation. Maybe like you're looking at the relationship that looks like a correlation. It is a correlation, sorry, but looks like a causation, but it actually happened to be the result of other correlation or causal relationship. So in this case, for example, like we have the working years and the age, and both of them have relationships or correlated relationship with income. But then it turned out working years and age also are correlated one another. So in that case, what happened is if the age is the one actually have something to do with income, then when the age increase, of course, income increase, but also working years happen to increase, right? Because age and working years are related, are correlated. So that means working years, if we are looking at just working years and income, as if like working years is causing income to increase. And we can see like the opposite way as well. For example, maybe like working years is the one important to have the effect on income. In that case, when the working years increase, then age also automatically increase because they have the correlated relationship. And then if we are blinded and then like just focusing on age and income, then as if like because age increase and then income also increase. Okay, so in that case, what are we gonna do? Like, well, how can we solve this problem? Well, it's actually when you think about it, okay, how about we break the relationship between working years and age? How we break that? Well, we can hold age constant. So only let's say like 25 years people, right? Like we just have those folks, or maybe 30 years people, employee, and then find the people who's 1 year working years and 2 working years or something. Then is there any change in income, right? And if there's any change in income, that case, we can at least say like, okay, working years and income has some kind of relationship there because age didn't move. Age is the same age, but the working years moved and then income moved. So that means there's some kind of relationship there. Well, you can keep asking like, well, how about others, factors? Well, that part we can't solve that, but at least we can kind of organize, okay, in this case, not the age, it's actually working years have some kind of effect on the income, right? And opposite thing too. So if you want to know, like if there's a really like relationship between age and income, that case we let age change, but we don't. We hold working years constant. In that case, when the age moves or like increase or decrease, the income also increase or decrease. So that's the kind of thing we can do. This kind of statistical running model can do. And we call this type of analysis called multivariate analysis because we are dealing with multiple variances, multiple variables. And this requires to use a statistical learning model, but not machine learning models. That means these are green things. Okay, so not like random forest or XGBoost type of machine learning model cannot do something like this, but linear regression, logistic regression type of statistical learning model can do. And then let's go back to this view here, go back to the analytics. So because this coefficient tab shows up only for the statistical learning model, but not like random forest or other machine learning model. Then here is, so that's the mystery resolved because, hey, this gray line, that's the actual value. So like I said, like age and then monthly income seems to have some kind of relationship. But the prediction line, we look at it, is like a super flat. It doesn't matter like whatever the age could be because it's always the same amount of income. And that's because the way of thinking here is that when all the other variables hold constant, stay the constant, that means the job level is the same, job role is the same, working years is the same, but only the age is different. And 1 year, age is increased, how much of the salary or income increases in this data? And the answer is coefficient -3. So -$3 decrease. And -$3, the $3 is like, what are you talking about? This salary here in the $1,000 to $20,000 variance, $3 is like, not much of a change. It's not even significant. And that's what we are seeing. That's why this is gray. Okay, so if this predictor variable, if I select only age, then age is going to become significant. And you're going to see the prediction line to be kind of like go along with actual data. But when I include the job level, job role, total working years together, then that means you're going to see only the age independent effect on the prediction. And in this case, which is basically nothing. So this is actually pretty great because then we can see, okay, so job level, even like job role and working years, age, those are the constant or didn't change. But if the job level change, okay, this much in this company, this much of the salary income will change. So that's the multivariate analysis. Okay, so that's the, whatever that could be, we build this linear regression model. And then the last part, we have the model, can we use it? So this one kind of, just to summarize though, when you go here, this is like I said coefficient. Based on this coefficient, there is a formula of as a prediction model. And can we use this prediction model to predict? So I have imported this like 100 employee data separated as a separate data frame. Okay, and then can we predict, and this data happen to already have this monthly income, but let's assume this data doesn't have, or maybe like I'm gonna use this one and predict it and compare the actual value and the predicted values or something. Okay, so in that case, here, right-hand side top, there's a plus button. Click on the plus button, and then there's this predict with model bracket analytics view. So that means we're going to use the model we created under the analytics view. You can use the model from any data frames. So okay, if I select it, then first thing you want to do is you got to select the data frame. Like in this case, employee data. This is where I created that data model, and prediction model. And which analytics model, I have created only one. So like I can select only one. If you happen to create like linear regression or random forest and other things, you can select that as well. And then I'm going to click run button. And what this is going to do is like this is going to provide pass that 100 people's data to the linear regression model. Linear regression model will apply that formula to that data and then come up with a monthly income. Let's see. And then that's done. And then the newly added column, these are the 4 columns. The important thing here is the predicted value. So these are the numbers that are predicted by the linear regression model that we created here. Okay. All right. So that's pretty compacted. Oops, where's the slide? Okay. Compacted seminar, but I think that's all for today. It's already good timing to stop. Okay, so that's it for today. So this is how you can start using analytics, and obviously there are a bunch other analytics as well. So you can find other analytics. So like how you can find it, if you're interested in more or want to go to the next step, is when you go to the LAM and then go to the training seminar seminar menu, and then select the seminar, the detail. So then this will jump to the seminar page. Okay. Then when you scroll down to the bottom, it says past seminar, and then check out the past seminar. When you click on this, and you can see all the recording we have done in the past. And then notably, I would recommend is here the factor analysis and the text analysis. These are 2 analyses that also you can do under the analytics tab here, like I'm talking about text analysis and also the factor analysis. So these are important, useful, especially for like you have the survey type of the data. And then when you go scroll down, like you, for example, here, the time series, that's a time series prediction model as well. And then also, like if you want to know, go into more about, for example, correlation and variance, then you can go to this seminar recording as well. So there are a bunch of the seminar in the past, and so I would strongly encourage you to take a look at those as well. Okay, so that's it for today. And otherwise, you can also go to how-to tutorials and how-to video if you wanna know more about how to use Exploratory. Okay, so with that, and next week I'm gonna cover the last part, the part 4 of how to use Exploratory series. I'm gonna walk you through how to create reports or like a dashboard and note in Exploratory. Okay. All right. So thank you so much for joining. And then with that, I'm going to end this seminar today. If you have any question, please feel free to contact me like a can@exploratory.io. And otherwise, I hope to see you next week. Bye.